All right, so we have our first sort of intro lecture here for Chapter 9, which deals with molecular shapes. So before I get started, just wanted to let you know that we have some guest observers today. Didn't even notice this till I got everything set up, ready to go, but this is courtesy of my kids. They left this here for us. So if you know who this is, special bonus points for you if you know who these crazy guys are right here. But they're going to be watching Chapter 9 today. They're interested. Okay, so we're going to look at bonding theories and electron shapes. So before we get into that, electron shapes are sort of governed by electron domains. So an electron domain is a group of electrons. So these electrons could be bonding or they could be non-bonding electrons. So an electron domain could be bonding, and also an electron domain can be non-bonding electrons. Okay, so what we mean by that, let's take a look at a couple of examples here. So we want to figure out how many electron domains we have on the carbon atom here. Okay, so group of electrons. So we have 1, 2, and 3 electron domains. So if we look at the makeup of our electron domains, we have 2 single bonds, and we have 1 double bond. So if we add that together, we have 3 electron domain on that carbon atom. Okay, so notice we did not call this 2 electron domain. We called it 1 electron domain. So let's kind of think about it. We're going to be making different angles and shapes by spreading out these electron groups. But if you kind of think about it, a double bond, because it's between carbon and oxygen, these ones can't be spread out, meaning I couldn't take this bond and move it down here. They're locked together in position between this carbon and this oxygen. So because of that, they count as one single domain. So 3 electron domain. Okay, so we have another example here of water, O, H, and H. So if we look at this, we have 1, 2 electron domain that are bonding, and then we have 3 and then 4 that are non-bonding. So if we tally up what we have 2 single bond, and we also have 2 lone pairs of electron. So 2 single bonds and 2 lone pair. If we tally this together, we have 4 total electron domain on that oxygen atom in our water molecule. Okay, so that's how electrons domains work. So we've seen all of the examples except for one. So notice we can have single bonds as electron domains. We can have a double bond as an electron domain. We can have lone pairs as electron domain. So the last one we're missing is a triple bond. A triple bond would be a single electron domain, the same way that a double bond is. Okay, so when we start making molecules, we're going to make different types of shapes. Okay, so the way or what we use to make molecules, this theory is called the valence shell electron pair repulsion theory, or VSEPR for short. So what that means is that electron domains will maximize the distance between each other. So they are going to spread as far apart as possible because electron domains are made of electrons. They repel, so they're going to maximize the distance between them. Okay, so when we talk about the shape or the geometry made, we have 2 types. First, an electron domain geometry. So for this one, we include every single electron domain and we place them as far apart as possible. So for, like I said up here, we would figure out what shape we would make to place all 3 of these as far apart as possible. And then for our shape down here, 1, 2, 3, 4, we'd place all 4 of those as far apart as possible. And that's called the electron domain geometry, where, again, it doesn't matter what the electron domain is, we treat them all identical. For a molecular geometry is just the arrangement of the atoms in a molecule. So we take away the lone pair as an electron domain. So that's not to say we take these away and then figure out a shape with just two. We first use the electron domain geometry to get everything as far apart as possible. And then we just essentially, after we get our angles and our shape, with all of the electron domains, we just then consider only the bonding groups to give us our molecular geometry. Okay, so we'll go over the differences between the two in just a minute. Okay. All right, so we're going to move now. Oh, there's my ceiling fan. Let's see if we can get this better. All right, I'm going to turn the light on. Second. All right, see if we can get this a little bit better. All right, so you get to see my ceiling a little here. Maybe we can go a little bit angled to not see my ceiling. Well, all right, you get to see the top of my ceiling a little bit for this. All right, so we're going to look at molecular shapes in these slides here. So first, we're going to go here to the different types of electron domain geometries we can have. Okay, so our central atom and then how many electron domains we have. So we have up to 6 bonding groups or electron domains that we can have on a central atom. So we have 2, 3, 4, 5, and 6. So these shapes here are the different types of electron domain geometry you can have. So if the question on the homework or on a test asks you, what is the electron domain geometry of blah, 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 it has to be one of these here. Okay, so our choices are linear with 2 electron groups. We have trigonal planar with 3. We have tetrahedral with 4. We have a trigonal bipyramid with 5, and then an octahedral with 6. Okay, so linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. Okay, so they are all here. This slide comes from your book. So we have linear. So if you have 2 electron groups and you want to place them as far apart as possible, the best angle you can get is 180 degrees like we have right here. Okay, next if we add one more, if we have 3 electron groups, to get them as far apart as possible, we adopt this kind of Y-shaped here, which is called a trigonal planar, and these are 120 degrees apart. So next, so these ones are all in a plane. So we're able to maximize our distance between atoms in a single plane for these 2 shapes. 4, 5, and 6, we're going to be 3-dimensional. Once we add 4, we use all 3 dimensions of space and we get the tetrahedral. This shape gets its name from the shape it makes. If you connect all of the nuclei here, you get a tetrahedron. So tetrahedral has bond angles of 109.5. Trigonal bipyramid, this is a little odd. So this one is kind of like a Y shape here. So this is right here in this plane. Those are all 180. And then it's almost like you took this linear thing and then poked it straight up and down onto this. So that's here, up and down. These are essentially from this one to this one is 180. These ones are all 120. But to go from this one to the one in the plane is 90. So we actually, in this shape, have 2 bond angles when we're going from what I like to call the axial to the planal. So axial position, planar position, that's 90 degrees. Within the planar position, those are 120 degrees. And then finally, we have the octahedral. So in the octahedral shape, we get an octahedron. If you were to sort of connect all of them, we get what's called an octahedron. So we have 1, 2, 3, 4 in the planar positions, and then 1, 2 in the axial, with every single bond angle being 90 degrees. So this is like a traditional coordinate plane system. So X, Y, and Z we have here. Okay, so these are not the easiest things in the world to see. So we're going to look at some examples here. Okay, so linear, that was our first shape. So here is a linear molecule. So you have your essential atom right here, and then you have the other two atoms as far apart as possible here. Okay, so our bond angles for the linear shape, 180 degrees. Okay, so that's this guy here. All right, next we have trigonal planar. So just kind of as I've drawn it there, that's this one. So your central atom, and now if we add another electron group here, we spread them out even further to get 120 degrees. Okay, so that's this one here. All right, next, sort of moving down, we have the tetrahedral. Okay, so that's this guy here. So if you're kind of a more three-dimensional person, hopefully this kind of helps. So this is what a tetrahedron looks like. So all of these are entirely equal. So I can flip it around and twist it, and again flip it around. All of these are identical. Okay, so they're all that 109.5. So I'm going to write that on here, 109.5 degrees, our bond angles here. Okay, so how we draw this, because this is three-dimensional, how do we show this on paper? So I have it here with wedges and dashes. So I've drawn it exactly like this on the paper. Okay, so I put these ones all in the same plane, so they have the regular lines. They're all in the plane of the paper. And then the wedge is one coming out at you, so that's this guy here, and the dash is the one going behind you. So here, if I tilt it just a little bit like this, that's my wedge right here, and this is my dash right here. Okay, so that's how we draw these in 3D. This one is all in the plane, and we have to show that there is one poking out forward and one going back behind. So this is our tetrahedral. So I'll put it there just like this. Okay, so this is the fun one. This is where we have lots of different bond angles here. Okay, so this one here is 120, and then this one here is 90. So we have two. Okay, so here is this guy here. So I'm going to put it like this to start with. Okay, so this looks just like this, our trigonal planar, and that's kind of what it is. So we have sort of a trigonal planar shape in the plane right here. So these are all 120 if we're looking down. So these guys here give us those 120 degrees degree angles when we look down. So then, of course, I have the one up here, and I have the one down below. So then if I twist this way, you can see how I've drawn it here on the page, where I have all of these three in the plane. So plane, plane, plane. Then I have a behind one, which is right here. And then I have a forward one, which is right here. And if you look clearly, this is our 90 degree, which I've shown here. And then again, if I flip this up, there is my 120 degrees right here. So this is called a trigonal bipyramid because it makes a pyramid up here. And then if you flip it down, you can make a pyramid shape down here below as well. So this is our trigonal bipyramid, again, with our 120 degree angles and our 90. So again, our 120, if I flip this up, you can see then the 90s. That's Pilgrim, he says hi. Okay, so last one we have the octahedron. So the octahedron, it looks just like a coordinate system here. So the way I've drawn it is like this. Okay, so these ones up and down in the plane. Then I have two poking forward, these two, and I have two going behind, which would be these two here. There's other ways to draw it. Some people draw it like this, where you have 1, 2, 3, 4 in the plane, one coming forward, one going behind. However you do it is fine. I like to draw it this way. It doesn't really matter though, because I don't know. It seems like why not use the wedges and dashes? It's fun. So these are my wedges here, and my dashes are behind over here. So these are all, again, if I flip this around, these are all 90. So no matter how I flip this or turn this, we have 90-degree bond angles here in this shape. So these are all 90 degrees. Okay, so these are all of the different shapes we can make with our different electron domains. Okay, so if I flip this over, let's go back and see what we have. So we have our CO3 2 minus, our carbonate. We have the 1, 2, 3 electron domains. We look over here, 3 electron domain is right here. So this would be our C, our oxygen, oxygen, oxygen. So we have trigonal planar as the electron domain geometry. So our electron domain geometry, trigonal planar. So that's our electron domain. What about for water? So we have the 1, 2, 3, 4. Again, we're not distinguishing between any quite yet. So 1, 2, 3, 4. If we go here and look for 4, that would be here. So we have our oxygen. We have a hydrogen here, and then these two positions would be taken up by the lone pair on oxygen. So we'd have a lone pair here, and we would have a lone pair here. So for electron domain, for water, tetrahedral. Okay, so our carbonate would look like this with its 3 electron domains, and the water, kind of crazy, would look like this, where again, these two are bonds, so these would be hydrogens at the end. These two would be lone pairs. So to make the distinction here, we can put little hydrogen atoms at the end. Okay, so hydrogen atoms here, and then here, those are the lone pair. Okay, so we still give them all a position, just like we did here. Okay, so tetrahedral. Okay, so that's that. So what about then molecular geometries? So to get a molecular geometry, we're just looking at taking lone pair away and seeing what different shapes we make from that. Okay, so we're going to go back. We're going to look at each geometry, and we're going to see what types of molecular geometries we can make from that. Okay, so back to my ceiling. Here we go. All right, so for linear, with, again, the 2 electron domains here, there's really not any sort of side shapes you can make. If it's linear, you have the 2 bonding domains and 0 non-bonding domains to get that nice linear shape. There's no, say, replacing this with a lone pair and changing the shape. Okay, if you take this off and this is a lone pair, it's still linear. Then you have a diatomic and it would still be linear. Okay, so nothing fun really there. Our trigonal planar shape, this guy here, there are a couple of shapes we can make. So when we have 1, 2, 3, like we have here, when they're all bonding, we still get that trigonal planar shape. But what if we had something where one of these was a lone pair? So I'm going to make lone pair green so we can kind of see. Okay, so that's my lone pair. Okay, so when we're looking at just the molecular geometry, we know that that lone pair is there taking up space, but when we want to see what the actual sort of bonding scenario is, we kind of just remove that and we see what's left. So we know this space above right here, that's where those electrons are at, but when we remove those and only consider the bonding angles, we get this right here. Okay, so this shape is called bend. So we've shown that, again, it is the trigonal planar parent geometry. One of those electron domains is a lone pair, but in terms of the molecular geometry, we only show it as bend. Okay, so next we have the tetrahedral. Okay, so here. So next we have 4. We know tetrahedral is the parent geometry. Okay, so that's there. So when all four of them are bonding, we get the tetrahedral shape. Okay, so just like that. So now we can have two different varieties of this. Okay, so I said that lone pair would be green. So our next shape here, we're just scrolling down. What if one of those bonding domains was a lone pair? So what if we had three bonds? So 1, 2, 3, and then that lone pair at the top. So we would get this still 4 electron domain, but then we remove it and we have what's left. Okay, so kind of looks not entirely different from a trigonal planar until I move it sideways, and we can see that this is in fact not planar. So this is called a trigonal pyramid. So when I do set it down, you can see that the top is raised from the bottom here to make sort of a pyramid, okay, where these are not all flat and planar. Okay, so that is the trigonal pyramid, where again, 3 bond, and then we know that lone pair is up here taking up space, but when we name the molecular geometry, we remove it and just have this. Okay, so the last one, what if we had 2 bonds and 2 lone pair? So like this, those 2 lone pair and 2 bond. Okay, so still our nice tetrahedral shape with our 4 electron domain, but now once we remove those lone pair, we end up with this. So we've seen this one before. This one isn't entirely different from this one here. Only difference is this angle is closer to 120 and this angle is closer to 109.5. But essentially still the same shape, which is why we call them both bent. Okay, so these are the shapes we get from the tetrahedral. Okay, so next, what about those sort of really interesting shapes we had? All right, we're going to start with the Trigonal Bipyramid. So remember this guy? So with the 120s and the 90s. Okay, so here is our Trigonal Bipyramid. So when all 5 of the domains are bonding, we get the Trigonal Bipyramid. Okay, so what if we start putting lone pair in? Okay, so there is something to note with this. Lone pair, it turns out, take up much more space, which doesn't seem sort of likely, but it is true. So these are more diffuse lone pair, and they've shown that in the picture here, where bonding groups are sort of more confined between 2 atoms. So we put lone pair into shapes with more space. So if we were going to have a lone pair on this, it always goes in the planar position. You get 120 degrees between your electron groups here. If it's here, it's at best 90 degrees from everything. So lone pair go in the plane. Okay, so I have this shape, same as here. Okay, so we put that in here. And then for the actual molecular geometry, remember, we kind of ignore it. Okay, so we do know that there's a big giant lone pair there, but this is what's left. So this is called seesaw. So I'm so glad I have this so you can see. If I just flip this over like this, the seesaw comes from this, where you have the 120s down here, and the 90s could be like 2 kids sitting on here seesawing. So seesaw, seesaw, seesaw. So that's what you get, again, where we had that lone pair would be right here, that big sort of diffuse lone pair. For the molecule, we take it off and we just consider this. Okay, so what if we have 2? Okay, so we're going to add another lone pair. So again, it's going to go in the plane also, always in these 120 degree angles. So we get this. Okay, so this is our electron domain geometry. For our molecular geometry, I'm just going to remove them so we can just consider the bonds. So this one is called T-shaped, and that's because, if I flip this guy around, it forms a nice T. So remember we have that that lone pair here, then we have some pointing down into the computer screen, but it forms a nice T-shaped where all of these are sort of in the plane here. So that is the T-shaped. Okay, so our last scenario is what if we had now 3 lone pair? Okay, so if we have 3 lone pair, again, we're going to put them all in the plane to get them those nice 120-degree angles. And then if we look at just the bonding group, so we take away the lone pair, 1, 2, 3, we're left with this, where again, this plane is packed full of lone pair, but we're left with a linear shape. Okay, so 2 bonding groups, 3 lone pair gives us a nice linear shape. Okay, our last one. So this isn't all the shapes that can come from this, but these are sort of the big ones. So we're only going to look at having 2 lone pair in here. Okay, so when we have all bonding groups, we get the octahedral. This is this guy. Okay, so what if we put a lone pair in? Okay, so it doesn't matter, all these positions are the same, but to make it look just like the picture, I put it down here at the bottom. Okay, so that's what we get. Lone pair, bond, 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 bond. Okay, so if we want the molecular shape, we take that off, and we get what's called a square pyramid. So we would have a square base, and we could have triangle faces to build a pyramid here. So it's called a square pyramid, where we have 1, 2, 3, 4, 5 bonds. And then below, where I'm setting this on the computer screen here, that would be the lone pair. Okay, so last, we have 2 lone pair. So notice we put them as far apart as possible. So I wouldn't want to put this lone pair right here and get these at 90 degrees apart. I'm going to put it up here. We want to get those lone pairs as far apart as possible because they are so large and because they do repel one another so much. Okay, so we have this here. We take those off. What's left is the square planar. Okay, where I would have a lone pair up here and a lone pair behind. So my 1, 2, 3, 4 bonding groups like we see here, and then a giant cloud of lone pair up here, and that second lone pair down here at the bottom to give us our square planar shape. Okay, so these are the molecular geometries. So quite a bit more because when you start putting in those lone pair, it does change our shapes. Okay, so let's go back to our 2 examples here where we have the, carbonate and the water. Let's turn the light on. Okay, so we have our electron domain geometries for these. Let's see what the molecular geometries would be. Okay, so if we look, we don't have any lone pair here. So we have Trigonal Planar. All of them are bonding. So like we have here, 3 bonds, 0 lone pair. So they are going to be the same. So the molecular geometry is going to be the same at Trigonal Planar. Okay, so hopefully that makes sense because, again, there are no lone pair here. So these 2 geometries, the electron domain and the molecular, are going to be the same. That's not going to be the case here. Okay, so if we look at this, we definitely have lone pair. So let's take a look at what we have. Okay, so if I bring this up, here, let's bring this up. We have the 4 electron domains. If we look, we know that for water, 2 of them are bonding, 2 of them are lone pair. So if we look for that scenario, we have 2 bonding, 2 lone pair. That gives us the bent shape here. Okay, so that's this one here, 2 bond, 2 lone pair. Okay, so water, here. So water is this one right here, 2 bonding groups with 1, 2 lone pair. So this one is bent. So water is bent. Okay, so that's how this works. Okay, so one more thing to end this here. When we get into organic chemistry, it turns out you can have a lot of different shapes in the same molecule. So all of the things that we have here, like a lot of these have different geometries around them. So we're going to go through and look and see what we have. Sorry, switch this out. Okay. So, all right, so let's get started looking one atom at a time. So we're going to start with the carbon. So I'm going to give it a little circle right here. So we look inside this carbon, or at this carbon, we have 1, 2. We have 2 electron domains. So we do know that 2 electron domains is going to give us a linear shape. So this carbon here is linear. If we look at the one next to it, we have essentially the same thing. So I'm going to circle it in the same color. So we have that triple bond. And then we have that single bond there. So 1, 2. Again, no lone pair, nothing else. So this one's also linear. All right, that carbon next to it looks a little more interesting. So we'll circle it with a different color. So this carbon. Okay, so we have that. That's common between these for the electron domain. We have a double bond. And we have this single bond right here. So we have 1, 2, 3 electron domain with no lone pair. So this is trigonal planar. Okay, so that carbon, trigonal planar. Okay, so the carbon next to it looks a little bit different. So I'm going to circle it. Okay, so we have 1, 2, 3, 4. So 1, 2, 3, 4 electron domain. So 4 electron domain. This is tetrahedral. Go down here. So we have tetrahedral geometry around there. And if we finally look at our last one, so that oxygen, we have 1, 2 bonds. Then we have 3 and 4 with lone pair. So it's tetrahedral. But if we look at the molecular geometry, this one is bent. Okay, so if we look at this molecule here, we have a portion of this molecule that is linear. We have the middle section, which is trigonal planar in geometry. And we have the end of it, which is tetrahedral and bent in geometry. So how does this even sort of work? All right, so I built it. So this first part is kind of what you'd expect. So we have the carbon. I think I'm missing a carbon actually. I am. Sorry about that. Here, put this guy in. All right, got it. All right. So the first part is linear. So I have my hydrogen, carbon, carbon. So that's that first section here. The next one is trigonal planar. So that is this right here. So here, let me flip it this way for you. Okay, so all of these are in a nice plane here. Okay, so you can see all planar, linear, linear, and trigonal planar with our 180-degree angle, 180. This one here, we get the 120. And then we get to this carbon here, which is tetrahedral. So if I try to lay this down on the paper, this end of the molecule is no longer two-dimensional, it's three-dimensional. So the best I can do is kind of get it this way. Okay, so this one here, this carbon with the 2 hydrogens, which I have here in white. So that carbon bonded to 2 hydrogen, bonding to the trigonal planar carbon, and then bonded to an oxygen, which I have here in red. Okay, and then the oxygen having that bent shape here at the end. So this part of the molecule is planar, and this part of the molecule clearly is not. And again, you can see when I try to just set it down on the page, not so much. So you can have different geometries all within the same molecule, and you see this quite a bit in organic chemistry. And as you move through that class, whether something is, say, planar or three-dimensional, and these geometries is going to really affect how they react with different things. Okay, so here's a nice, again, example of that. Okay, so to end this section up, for practice, you should do do the Lewis structure for ICl4-, which may or may not have been done in the notes from the previous chapter. Okay, so 1, find the Lewis structure. 2, determine the electron domain geometry. And 3, the molecular geometry. Okay, so find the Lewis structure, or write out the Lewis structure, your electron domain geometry, and the molecular geometry. For the answer to this, go to the slide in the Prezi that we've been looking at while doing this. That's called iodine tetrachloride ion. It will give you the Lewis structure, the electron domain geometry, and then finally the molecular geometry. Hey, it doesn't give you the name, so make sure you can, it'll give you the shapes. Make sure you can match that up with the charts given in the Prezi and in your textbook to make sure you can figure that out.